1 and 2 from chapter 15. To this point, I think I've assigned up to question 36. Let's start with questions from homeworks. Claire. 28, you say?
Yeah.
Sure. So 28 says, find the exponential function that satisfies yada, yada, yada. So this is basically a half-life problem. So I would start by writing my model for population. Find the function. So we just need to fill in the numbers here.
Okay.
So our initial amount is 17. Since it's halving, the value for R is, there's a sale and it's half off. What percentage? 50%. But since it's off, it should be negative 50%. Very good. And this is the half-life is happening every 32 hours. So let's make our t in hours. So how many half-lives occur in 1 hour? 1 over 32, right? 1/32 of a half-life. So I'll write here t over 32. And then I'm all done. Does that feel cool, Claire? And if I wanted to, I could simplify the 1 plus negative 50 to over 100 as 1/2. That'd be fine also, or 0.5. That'll simplify all the way down to that. Victoria. 34. Sure, the number of grams of carbon-14 denoted C present in a certain substance after T years. I'm assuming that's supposed to be years. Or maybe this is a new unit of measurement. Is a years? Or maybe that's a yaz? Anyways, I was trying to make a joke, so nobody found it that funny. Okay, good. Is given by the function yada, yada, yada. Use the equation to estimate the half-life of carbon-14. Okay. So what I'm going to do is I am interested in knowing the initial amount. When is at what time would we have the initial amount of carbon-14? Zero, right? So if I do C of 0 and I type that into my calculator, I get 20. So what I know then is a half-life is going to be when there's half of that left. So I'm interested in the time it takes for that carbon-14 sample that's 20 units to decay down to, it's grams, excuse me, is the unit, to decay down to 10 grams. So that's the equation I want to solve. Cool with that so far? Very good. Okay, so fire up the old graphy McGrafferson here. 1231216 times x. Get rid of u. So there's that. Reset my window. I don't know how long a half-life of carbon is. Maybe we'll start with 100, see what we can see. The y minimum, I'm going to go 0. The y maximum, 20. That's how much we start with. So let's see. There's my line for 1. There's my half-life line. It's going to have to be a heck of a lot bigger than 100, right? Well, I'm going to make that then, I'm going to go 10,000 because that was not moving very fast. So there's that. There we go. So I'm looking for that intersection. Second trace, intersect command. Enter, enter, enter. 5,700 time units. And I think it was the time unit we had here was yees. Whatever a yees is. I'm going to stick with this joke and just kind of keep hammering it away. Yeah, it's, well, I mean, it depends on the problem. Some problems are measured in years. This one is measured in yees.
Can you have the test say yees, like the final?
I mean, we'll try.
What number was this?
What number was this, Victoria? This was 34? Yeah.
Can you explain when you know 10 equals 20, can you explain where the 10 is?
Yeah, so it's asking to estimate the half-life. So we knew initially we started with 20. So the half-life is going to make it, bump it down to 10. We want to find how long it takes to chop that in half. So that's why I used 10 there. Victoria?
Like when we're looking for like years, like some of the questions you ask, like what year, how do you know like what to round up?
Okay. Yeah, so if you have, it's about how you would answer the question. So like, say if it said, in what year? You could say, and say it was like, T is years after, like 1700. And your answer was like 57.2. You could say as an answer, you could say during the year, 1757 would be fine. Or if it asks, what's the first year? You would have to say, okay, then that would be 1758. So it just kind of depends on the phrasing of the question. Like if it's asking when is the first year that the population is blah, 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 then you need to round up. Okay. If it says in what year is the population, da, 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 you can say during and then like, and round down. It just kind of depends on like the phrasing of the question, I suppose. Does that make sense?
Yeah.
Yeah, so it's not like a math rule. It's just like, it's a grammar thing of like, what is this question actually asking? Is it asking for like, you know what I mean? Does that feel okay though?
Yeah.
Okay. Ben. Sure. Easiest question I've had all day. Jack.
30.
Sure. All right. So it says the 2000 population of Las Vegas, Nevada was 478,000, was increasing by a rate of 6.289% every year. At that rate, in what year will the population reach 1 million? Okay. So again, we'll start with our population model. So we're going to have to write our equation. So our initial amount is 478,000. our rate of change is 6.289. And that's happening every year, so I can just leave it as t, where t is in years, right? And and we're interested in the time when we get to a population of 1 million. So that's what I'm going to be solving. So to do that, I'm just going to go to my calculator. So the left side, I'm going to make 1 million, 3, 4, 5, 6 zeros. And 4, 7, 8, 1, 2, 3 times 1 plus 6.289 divided by 100 to the x. So I'm going to go ahead and reset my window now. I don't really know how long it's going to take to basically double in population. I'm going to guess it'll be 100 years or less, but we can always, go ahead and move it out. That's a long time for a city. My minimum population would be 478. I'll make it a little bit less than that. Maybe I'll just call it 400,000. My maximum population I'm looking for is 1 million, so I'm going to do a little bit more than that, maybe 1.25 million. Okay, and let's take a look here. So there's my 1 million line. Here's my population. Well, that happened a lot faster than I was expecting. Second trace, intersect command, enter, enter, enter. So 12.1. So it says, at that rate, in what year will the population reach 1 million? So this is time 0 is 2000, right? So I would say during the year 2012. 2012 was the end of the world. What are we doing now? Is this like heaven? It's kind of disappointing for heaven, right? It's a little bit of a disappointment, isn't it? Heaven is math class for eternity. Maybe we didn't end up in heaven. Or maybe it's a reincarnation. We're just going to relive like Groundhog's Day style, just relive this day every day.
That would be fun.
It'd be something.
I love time loops.
Time loops are fun.
Yeah.
Victoria, you're trying to ask a question here?
I do.
How do you find like the maximum of like the maximum?
Yeah, so on those questions, it's always talking about a logistic, so something that looks like this. And remember, for a logistic function, they're all going to be of the form like this or that. So all of them have a lower bound as a horizontal asymptote y equals 0. And they all have an upper bound, a horizontal asymptote of y equals c. And that is going to be your maximum sustainable, that upper bound. So it's just going to be the numerator, is what's going on there. But that's like a feature of all these logistic functions, and that's why they're often helpful in modeling like population behaviors, because you can only get so big before like you filled up all the space you have or used all the resources you have. You know what I mean? Like if your city is zoned for like this many square miles and it's all been developed, it's hard for the population to get a lot bigger because there's no other place to build houses or whatever. I mean, you can build up, you know, and have like skyscrapers and like everybody lives in an apartment. But I find it unlikely that you could fill in a, you know, like a 50 million person city that everybody's just living in an apartment. I mean, New York is kind of an exception there, but oh, they're gonna let you build down. You can have like mole people. I don't want to live in your city, Landon.
No restaurant district goes down.
It's gonna the apartment building's called the Ant Farm.
That'd be sick.
You live underground?
To the ant farm, yeah, that'd be so cool. It's have no sunlight.
Yeah, yeah. You'd have rickets and stuff.
Yeah.
Isn't that what you get from seeing the sun? All right. Any more questions on this stuff here? Cool. We're going to dip our toes into section 3 for a little bit, and then we're going to finish the rest of that up next time. Okay, today we're going to start revisiting these logarithmic functions. Reminder that this was a topic that we covered in our Algebra 2 class, but in Mr. Kulik's experience and his many years of teaching, this is one of the least retained topics in Algebra 2, so it's a good thing we're going to do it again. I mean, usually like the factoring and quadratic formula and stuff like that sticks okay. This is one that it's like in one ear, one out the other. Because it's
We had a formula of the song.
Yeah, you got the song. There you go. That's something.
I just remember the teacher said, there's like one thing that you remember from this class, would be this.
Yeah. Good. All right. The one thing you remember was not the teacher's name, but just that
I do.
it's like, hello, teacher.
He's not allowed to remember.
All right. So, logarithmic functions. Let's say we have this equation. We have 2 to the x is equal to 4. What's x? 2. Yeah. Or we have 2 to the x is equal to 8. What's x? 3. Right? But what if we have 2 to the x is equal to 6? I mean, is it 2.5? I don't know. Let's see how that comes out. Not quite. So, how do we do a problem like this then?
With log.
Yeah, we're going to be using logarithm. So what a logarithm is really answering is what exponent, or which is like, let's say what power of 2 is 6, right? That's essentially what we're trying to answer here. Everybody agree? So the name we're going to give that power is just going to be called a logarithm. Okay, so let's define this idea formally. Okay, so for some value of b that's positive and not equal to 1, and some value of x that's greater than 0, we say the exponential equation, b to the y is equal to x, is equivalent to the logarithmic equation, log base b of x is equal to y. We call that subscript b the base of the logarithm. So the other way to think about this is, what's the name of the number that goes in this exponent? It's this log base b of x. Right? Does that kind of make sense to you guys? Let's just get a little bit of practice with this definition. Okay with that? So let's say we're asked to evaluate some logarithms. Let's say we have log base 4 of 16. So first thing I'm going to do is I'm going to say, okay, let's say that the answer to that is x. Now I'm going to use the definition above to rewrite this logarithmic equation as an exponential equation. What would I have to write here? Yeah, so I have something like the green box above, and I want to rewrite it as the yellow box. So what do I write? 4 to the x equals 16. Everybody's cool with how I did that? The base of the logarithm is the base of the exponential, so 4 is the base. The answer to the logarithm is the exponent for the exponential. So x is in the exponent, and then the argument of the logarithm is the answer to the exponential, so equals 16. So then what is x in this case? Two, right? 4 squared is 16. Shout them out when you know them, guys. Don't be shy. Okay, let's do a couple more of these. So let's say we have log base 5 of square root 5. Well, just like before, I'm going to say the answer to that is x. That's going to let me rewrite this as an exponential equation. Who can tell me the exponential equation? 5 to the x equals square root 5. So what's x in this case? We're relying on a fact that we would remember from Algebra 2. Uh-oh. Jack, you're in trouble here. So in Algebra 2, one of the things we learned is that we can rewrite any radical as an exponential. So what is the value for x in this case for a square root? Not 2, 1/2, right? So in a square root, this is a 2 there. So it becomes the same thing as 5 to the 1/2. So x is just 1/2. Boy, those exponent rules we learned last year are sure important. Those would be good ones to have remembered also. Okay. So what if we have log base 3 of 1 over 27 equals to x? How do I rewrite this one? 3 to the x equals 1 over 27. Okay? Whoa, Boise, Mr. Gulak, that seems kind of hard. It's not so bad. What if we rewrite the 27 as 3 to the third? Now what does x have to be? We're using another rule from last year in our Algebra 2 class. You're like, oh boy, I wish I'd paid more attention last year. I didn't know these things were going to be used again. Come on, you knew they were going to be used again. So this is the rule in question, is that a negative exponent makes a reciprocal. So what is our value for x here? Negative 3. Very good. Yeah, I didn't hear that part after the negative. Well, you totally guessed right. So that's okay. Let's do another. Log base 12 of 1 equals x. We'll rewrite that as an exponential. So what's the equation I write here? 12 to the x equals 1. What's the value for x here? 0 is correct. Again, hopefully from last year, you remembered this property of exponents. Just as a aside here, what is, it says x to the 0 is equal to 1 for x not equal to 0. What's 0 to the 0? It's not 1. It is undefined. Yeah, it's one of those indeterminate forms. All right, one more, and then we'll kind of summarize some observations that we made here. So let's say we have log base 8 of 8. Well, let's write that as an exponential. So how can I write that? 8 to the x is equal to 8. So what does x have to be? 1. Everybody's cool with that? All right. So let's summarize some of the observations we've made here with some properties. First one is the log of 1 is always 0, regardless of what the logarithm is. Everybody's cool with that? Because it's just equivalent to saying b to the 0 is equal to 1. Now, remember when we did this property before, we said that that base of the exponential can't be 0. Why am I not worried about that condition here? Because when we defined our logarithm, we defined it for bases that were greater than 0. So not possible for the base of a logarithm to be 0, so we can't ever get something undefined. So we don't even have to worry about that possibility. Cool! Next up, log base b of b is equal to 1. That's what we observed in question E from above. Okay, neato. 3 log base b of b to the y is equal to y. Basically just saying that in exponential form, b to the y is equal to b to y. Whoa! Shocking. This is what we observed in questions like C, or A, B, and C. Everybody's cool with that? Okay. And then our last one, which is just kind of the inverse of what we're seeing in number 3. We'd say b to the power log base b of x is equal to x. If I rearrange this exponential into logarithmic form, it's basically just saying log base b of x is equal to log base b of x. If we were to note any of these properties that are the most important, most frequent to use, it would be these 3 and 4. Because essentially what these two properties are describing is how to use a logarithm or an exponent base to solve an exponential equation or logarithmic equation. So these two properties will be super useful to us moving forward. Okay. There are two special type of logarithms that we're going to make mention of. The first one is the common logarithm. So what we say, the common logarithm is log base 10. But we, as mathematicians, have decided that we're never going to write the base. We're just going to write as log with no base. And everybody's going to understand that that means that it's log base 10. So what's the logarithm's base if there's no base written? 10. So if I don't have a base on my logarithm, the base is, what's the base on the common logarithm? 10. I'm going to say it 3 times just so I make sure that everybody hears me, because this is like just a fact. But if you forget it, or you didn't hear it, or you weren't paying attention, it's kind of impossible to do anything with this. It's like, what's the base of the logarithm? I don't know. 1? Sure, I'll write that there. No, it's not. Again, the 1 can never be the base for a logarithm, or 0. The other logarithm is called the natural logarithm. The natural logarithm is log base e of x, and the way we write that is ln of x. And e, again, is that number we talked about a couple lessons ago, that 2.71, yada, 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 yada. Hi, Joe.
Hello.
Everybody's cool so far? So let's just do a couple of examples here. So let's say we want to evaluate log of 1,000. Well, let's say that equals x. And then we'll rewrite this as an exponential equation. What's the exponential equation I would write here? 10 to the x equals 1,000. So what does x have to be in this case? Not 10. 3, right? 10 times 10 times 10 is 1,000. A 1 with 3 zeros after it, right? What if we had log of 51.37? Yeah, what in the world do I do with that? There's nothing to do with this other than go to your calculator. So notice the log button, common log is right here. So I can just type into my calculator log of 5137. Whoop! There it is. So what is this 1.71 number meaning? That's the power of 10. That should give me 5137. Everybody's cool? So common log, the button is right there on your calculator. Right below the common log button is the natural log button. If I wanted to do the natural log of that number again, I just type it in. What is this number meaning? That's the power of e. That should give me 5137. Or if I wanted to do like log base 2, we can do that also. To get the log base whatever number you want, you press the math button and scroll all the way down till you find the log base command. And then you can go ahead and type in whatever base you want, like 2. Well, not whatever, any feasible base you would like. Obviously, the bases have to be non-negative or have to be greater than 0, not equal to 1, right? So if I do that, what's this 568 number saying? Well, it's the power of 2 that should give me 5137. Everybody feel good about how to get things out of your calculator? We get the idea how to do it by hand. Can we do every problem by hand? No, man. Has to be some clever way of rewriting, the argument inside the logarithm as some power of the base. Sometimes that's easy, sometimes it's not. And sometimes it's not even possible to really do it, right? Everybody's cool? Okay. This feels like a good place to stop. So at this point, we had done up to 36, so we can now do 37 to 68. So that'll be the next block of problems. That'll be due, though, that homework, the next homework check or whatever. Not Sundays, but the following Sundays. Since we won't have a chance to meet and talk about it before then. Although this one should be fairly easy. I think half of it is just typing stuff into your calculator and pressing enter. But still make it do that. We have a lot more stuff to talk about log-wise, but this is a good place to stop before we transition into something a little bit different inside of this log topic. So this feels good as a stopping point. What am I going to ask you to do now?